Hey, welcome back. Mr. Richardson here. It's been a while. I think the last time I saw you, we were doing a lab. But back today for some more notes. We are starting Unit 3. So we will get to that. All right, so working on Unit 3, which is nuclear chemistry. And our 3.1 unit is going to be alpha, beta, and gamma emissions. It's just one M in emissions, I believe. All right, so these are three types of nuclear radiation. I believe they're named after when they were discovered, alpha being first. It's the first Greek letter, like A, beta second, and gamma, believe it or not, is Greek letter C. I think it'd be G, but it's really Greek letter C. Okay, so a little bit of review first. So the nucleus of an atom contains protons. And here's the idea. Again, we draw them as a P positive. They repel one another. So if you have two protons, two positive charges, they're actually going to push each other away. They're going to, if all you have is protons in the nucleus isn't going to last. It's like two of the same sides of a magnet. They push each other away and not going to stay together. So luckily, we also have neutrons, which we symbolize as N0. They don't have a charge, and they help to insulate the protons. They kind of protect those positive charges. They also kind of act as like a force to keep everything bound together. And that's how our nucleus stays together, despite the fact that it's all positive charges in there. So here's our nucleus. And again, those positive charges are not so repel when you've got these neutrons in between them. And there's a kind of a force between the neutrons and the protons holding them all together. All right, so that's all pretty much a review. We've worked at that. Where are we going with all this? Well, atoms, small atoms. How do we find small atoms? A Z less than 20. So again, a little bit of review here from last chapter. A Z is the number of protons. It's the atomic number. So anything less than 20 has a 1 proton to 1 neutron ratio. Let's see if I can find my periodic table. It should be around. I should have been prepared slightly better. There it is. All right, so here's my periodic table. And as an example, take a look at carbon 12. Most carbon have a mass of 12. That's why the average atomic mass here is 12.011. Most of our carbons have a mass of 12. So carbon 12, 6 protons. We know that all carbon have 6 protons. And because it has a mass of 12, it also has 6 neutrons. So that's a 1-to-1 ratio. So that holds true for the first 20 or so elements. So up to about calcium. You see calcium, average mass of 40, 20 protons. That means most of them have about 20 neutrons. Magnesium, 12 protons, average mass of about 24. So most magnesium have 12 neutrons as well. So for most of our smaller elements, that holds pretty true. You have about double the atomic mass as the atomic number. As you start to get larger and larger atoms, the ratio grows or shrinks, I suppose, depending on the perspective you're looking at, to 1 proton to every 1.5 neutron. A 1 proton to 1.5 neutron ratio. So as an example there, lead 206. May not know that one off the top of our head. While we've got our periodic table, find lead. There he is down at the bottom here. So lead 206, 82 protons. And we can do the math here. 206 minus 82 means 124 neutrons. And that's that 1 to 1.5 ratio. There are 1.5 times as many neutrons as protons in this large atom of lead. So small atoms, generally 1 to 1 works. As the atoms get bigger, they start trending towards a 1 to 1.5 ratio. What this whole chapter is about is when that ratio is off, when it's not 1 to 1 or 1 to 1.5, 1.5. So when that ratio is off, the isotope is now what we call unstable. The nucleus is going to fall apart. We call that decaying. And that's what nuclear radiation is. If you've heard of nuclear radiation, that's an atom decaying. It's an atom falling apart. And that's a lot of what we're going to focus on in this chapter. We have, well, we're going to look at 5 different types of nuclear decay, just 3 today, and 2 more on our next day, our next visit. But the first type of decay is alpha decay. Alpha particle. And we symbolize alpha, well, as best we can. Greek letter kind of looks like this. A big loop there with the 2 tails. So that's kind of an alpha particle. It is comprised of 2 protons and 2 neutrons. For those of you thinking along at home, this is a helium nucleus. And I mentioned that because you're gonna see that helium nucleus here pretty soon. So 2 protons, 2 neutrons, it's a helium nucleus. The way that we symbolize it, 4, 2 helium. That's how I prefer to do it. I use the helium symbol. You're going to see it and you're allowed to write it as 4, 2 alpha symbol. Either one of these is perfectly all right, but you do need to memorize one of these 2. Well, both of them, because you might see this one, even though you like this one. But you do need to memorize these symbols because you're going to see them a lot this chapter. You'll be asked to produce them a lot this chapter. So 4, 2 helium or 4, 2 alpha. And what that looks like, got 2 neutrons, 2 protons, and then very important, it has a positive 2 charge. Keep that in mind. It's going to come up a few times. It is a helium nucleus, but there's no electrons, which means we have 2 positive charges. Nothing to cancel that out. No electrons go with it, just the nucleus. So there's 2 positive charge on alpha particles. Our next type of decay is called a beta particle. The Greek symbol for beta looks like our B, except it does have that tail. That's not me being careless and sloppy and adding a tail. That's supposed to be there. That's a beta sign. And a beta particle is an electron. In a video. So the way that we symbolize the electron, electrons have zero mass. And then we use this -1 because it's kind of like the opposite of a proton. So normally this number down here counts protons. The electron is like an opposite of a proton. It has zero mass. It has a -1 charge. So this is the symbol for a beta particle. I like the E for electron. You might also see it, and you're welcome to write it, for those of you who prefer to write in Greek, like a beta symbol. And the important part of the 0 and the -1, either one of these is an acceptable symbol. Now the beta particle is really pretty cool. It's a neutron. And while we're at the symbol for neutron, one mass, no protons, that's a neutron. And neutrons have one mass, electrons have zero mass. So what happens in beta decay? So neutron falls apart into a beta symbol, an electron. There's our electron, and the other half of a neutron. You guys can do the math here. No mass. We had one mass. So whatever the other particle is going to have one mass. -1 plus what gets us back to 0? That would be +1. What has one mass and one proton? Well, a proton does. Yeah, so a neutron actually turns into a proton by releasing an electron. So electron gets shot out of the nucleus, and that's what beta decay, or that's what occurs during a beta decay. The electron gets shot out, and now you have one more proton, one less neutron. You're adjusting that ratio. All right, our third type of decay. Gamma emissions. Symbol for gamma kind of looks like this. I don't know if you know cursive, but it's like an upside down L, so just a loop there. That's our gamma symbol. There's not a whole lot to gamma emission. They have no mass, no charge. That's why I said this guy was probably discovered first, called the alpha, the first. He's big, he's hefty, and he's got a +2 charge. Pretty easy to discover in chemistry. Beta particles are a little bit smaller, but they're still charged. Gamma rays have no charge. All they are is photons, little packets of light energy. So gamma rays are high energy photons. These usually occur with other types of decay. So you usually have gamma rays along with other types of decay. And again, there's no mass, no charge. So they're really pretty easy to work with. It's just 0, 0, gamma. We'll see an example of that in just a minute here. So there's our three types of decay. We have alpha particles, beta particles, and gamma emissions. Again, we don't call it a particle because it's really not. It's just a high energy packet of light, basically, that comes off of the decaying nucleus with one of these other particles. A couple of examples for you guys. First one. Right, the alpha decay of radium-226. And I'll be honest with you, this is what a lot of the test looks like. It's problems just like this. So there's a question, you're going to see some homework tonight. You'll see it on future homeworks. Again, this is a lot of what the test is going to look like. First of all, you need your periodic table. You guys are going to be getting familiar with some pretty large elements this chapter down towards the bottom of the periodic table. And so the first one we have to find is radium. Aha. There it is, number 88, radium. Now watch out, it's pretty similar to radon. We don't want radon. We're looking for radium. All right, so we're gonna go ahead and write that atomic symbol, Ra, for radium. There's the mass number that goes top left. And then we need the atomic number on the bottom left. Atomic number for radium, 88. All right, so here's our unstable atomic radius, and tells us it's decaying by alpha emission. So we need to memorize, if we haven't yet, we need to have memorized what an alpha particle is. It's a helium nucleus. There's an alpha particle. And now here's the trick. You want to balance the numbers across the top. So when I say balance, look at the arrow, and both sides of the arrow should be balanced. Again, think of a balance. If you have too much on this side, it's going to go down. If you have too much on this side, it's going to go down. You want it to be balanced just straight across. So we want to make sure both sides are equal. I've got 226 on this side. I've got 4 on this side. So 4 plus what? We get up to 226. 4 plus 226 getting me up. I'm sorry, 4 plus 222 getting me up to 226. Then we do the same exact thing for the bottom. Right now I have 88 on the left, 2 on the right. So 2 plus what gives me 88. We need a calculator for this one. 2 plus 86 gives me 88. Back to the periodic table. We need to find atomic number 86. There it is. Rn for radon. All right, there you go. You have written your first balanced nuclear equation. That whole thing right there. Write the beta emission of iodine 131. Okay, well, we're going to start. We were given iodine, so start with that. We're given the atomic mass of the mass number of iodine, which is 131. So that goes right here. I don't have I memorized, but I can find it on the periodic table. I know it's a halogen. It's over here. There's iodine, atomic number 53. Now he's going to decay by beta emission. So again, we got to think, what is a beta particle? It's an electron. We symbolize it 0, -1. And then watch out for this stuff. This is one of the most missed questions on the test. People oftentimes see the 53, they see the -1, they put 52. Don't do that. It's -1 plus what equals 53. So it's not 52 over here. I get 52 a lot. Don't put that. -1 plus 54 gives me 53. The numbers on top are pretty easy. We're working with a 0 there. So 131 on top, 54 on bottom. 54 is Xe xenon. There we go. That's our balanced balanced nuclear equation for iodine 131 by beta decay. Got one more example for you guys. We haven't worked with gamma yet, so let's take a look at gamma. So in the alpha decay of U-238, 2 gamma rays are emitted. So I mentioned we took a look at gamma rays. They're oftentimes with or accompanying another type of decay. So there's alpha decay. Let's start with that. So we've got U 238 up top, and we got to find U on the periodic table. Aha, there it is. Number 92 down here. So he's going to fall apart by alpha decay. Again, we got to remember what that alpha particle is. I like to write the helium. You guys are more than welcome to write the alpha symbol. Same thing, alpha particle, helium nucleus, same exact thing. We balance the numbers on top. 238 is equal to 4 plus 234. 92 is equal to 2 plus 90. And we got to find number 90 on the periodic table. There it is, thorium. Here's a big hammer. And then finally, the last step is we also have some gamma rays coming out of here. So our symbol for gamma, it's kind of that upside down cursive L that has 0 mass and 0 protons. So that's really easy. It doesn't affect how we balance the equation. And then one more thing, it says that there are 2 of them. So we write the 2 right there. Hey, all right. Generally, people like this unit, I think. Hopefully the notes help. Feel free to leave a comment. Let me know if they are or aren't. But otherwise, I'll be back on Friday with the next 2 types of radiation. Until then, see ya.